Welcome to the TILOS seminar. We are incredibly happy to have our very own Hamid Hassani giving the talk today. So Hamid is currently an assistant professor in with affiliations in 3 departments in UPenn: the electrical and systems engineering, the computer and information systems department, and the statistic department. So for some reason, UPenn has the names of the department all different from the standard thing. So instead of electrical and computer, they call it electrical and systems engineering.
Yeah.
Instead of Department of Computer Science and Engineering, it's Computer and Information Systems Department. Okay. And I know that the statistics department is in the business school. So yeah, Hamid is affiliated to all of them. I know Hamid for quite a few years now. He was a star in the information theory community. Since when he was a student, his results were well known, and his thesis was award-winning that got the Information Theory Society Thomas Cover Dissertation Award in 2014, I think. And then he won an Information Theory Student Paper Award, followed it up with a Simons Barclay Fellowship. He was like during his postdocs, he was there for some time. Then after joining UPenn, he has gotten multiple early career awards, including the NSF Career Award and the AFSOR, Office of Scientific Research Young Investigator Award. He recently also got the Intel Rising Star Award and was named a Distinguished Lecturer of the Information Theory Society. So Hamid has deep results in both information theory and machine learning. Today, he's going to talk about how distribution shifts are how they affect machine learning. So Hamid, the floor is all yours.
All right, thank you very much, Arya. Thanks everyone for attending the talk. So the talk will be about learning robust models, and I'd like to begin with mentioning some of the main applications where robust models are important for. And these are safety critical applications. Here by safety critical, I mean any application where the detections, decisions, and recommendations made by human designed systems would impact the well-being of humans. A canonical example would be, for example, self-driving cars, where detecting, let's say, pedestrians in a sidewalk would impact the well-being of those or safety of those pedestrians. There are, of course, many other applications and domains, such as robotics and medical imaging, where the interaction between humans and learning-based systems for these applications are subject to obvious safety-critical constraints. So the main message here is that machine learning systems, when deployed in safety-critical applications, must be robust and trustworthy. So let me now say a few words about this term robustness here and explain how we mathematically think about it right now in the field of machine learning. When talking about robustness, a natural starting point would be to talk about the phenomenon of adversarial examples. This phenomenon was discovered around a decade ago. However, it's now grown to its own field within the area of machine learning. And it can be simply explained as follows. Let's consider a standard supervised learning task, for example, classification, and a standard data set, for example.
Hamid?
Yep.
Sorry, I think we're still seeing the title page.
Oh.
Is that what it's supposed to be?
No. Okay. So let me, I don't know what's the problem. Let me share the whole screen and see. Let me share the whole screen.
Can you now try moving the slides?
Yeah. Do you see it moving?
Yeah, now this is fine. This is the slide we never saw.
Okay. So yeah. So motivation, it was safety critical application. What's important here? So there are like variety of these kind of applications. What's important is that our systems, the machine learning systems that we design, they should be robust and trustworthy. And I was just about to explain how we how we should start to think about robustness and how we should mathematically maybe develop this key term robustness here. And so a natural starting point would be the phenomenon adversarial examples that I'm just about to introduce here. So let's consider a standard machine learning or supervised learning task, for example, classification. So in order to do so, we have, let's say, a standard data set and a standard hypothesis class, for example, a neural net. And we train this neural net using this standard data set. Think of the data set as the data set, think of, let's say, MNIST, CFAR, ImageNet, whatever, right? So you train the classifier, for example, as a neural net here. And then at test time, we know that if the data point, for example, the image here, if the data point comes from the same domain as the training data, for example, if inside the training data, we have seen a few images of, let's say, the object inside this image, for example, this panda here, then at test time, on a newly unseen image, our model would be able to accurately predict what the label or the object inside the image is with high confidence. Okay, so here, the model that we trained using the training data would basically classify this data point as a panda. Okay, and that's just the success of deep learning or supervised learning that we have been observing in the last decade or so. Now, adversarial examples can be explained as follows. Let's take the same image. What we typically can do is that we can add a very small amount of noise to this image that can fool the model that we are using. Okay, so what this means is the following. Let's take that image and assume that we add to it a very small amount of noise. The choice of the noise can be made in a way that, first of all, the perturbed image would be indistinguishable to us as humans compared to the original image. And also, the choice of the noise can be made in a way that the perturbed version would be misclassified by the model that we are using. So in this case, for example, the perturbed image, the image that we have added a small amount of noise to, would be classified as a gibbon by the model that we are using. Of course, the choice of the noise should be adversarial. It has to be well crafted with respect to the model that we are using as well as the data point. But what's important here, as the phenomenon adversarial example, is that we can often add a very small amount of noise to our image, and that such that it causes misclassification. Now, let me dig a bit more into this phenomenon of adversarial examples. Typically, in machine learning, we treat data points as some points in some Euclidean space RD here. Now, around each data point, assume that we draw a ball of radius epsilon. Think of epsilon to be a very small number. Within this ball, we are looking for a noisy version of our original data point such that the noisy version is misclassified by the model that we are using. Okay, this noisy version that causes misclassification is called an adversarial example. And in order to find this noisy version, we really have to search through this small ball. So we need to solve an optimization problem. That's why it's called an adversarial example. So as I mentioned before, the main message here is that our modern learning-based systems, for example, deep neural networks, are highly fragile to these kind of norm-bounded perturbations. And this is now well documented within the area of machine learning. There are by now thousands of papers that talk about different properties of adversarial examples and also propose different algorithmic procedures to make our models against these kind of norm-bounded perturbations. Most of the literature so far on robust learning in the field of machine learning has focused on two very simple sets of perturbations. So the set that you see at the right, at the left, sorry, this L2 ball that you see here is one geometry of perturbation. So around each data point, we draw a ball, an L2 ball, Euclidean ball of radius epsilon. Within this ball, we look for an adversarial example. So the geometry here is very simple. It's just a Euclidean ball. Another geometry that has been considered and studied quite a bit for perturbation sets is the so-called L infinity ball. So around each data point X, you draw an L infinity ball of radius epsilon. Within that ball, you look for an adversarial example. And this value of epsilon is typically very small, such that the perturbed version of the image would be, for us as humans, so we cannot really distinguish it with the original image. Okay, so these are, as I mentioned, these are the two geometries that people have studied. The geometries are very simple. You can easily search through these kind of balls, and since they are very simple, people have studied them a lot and provided, let's say, theoretical examples and algorithmic procedures and so on. But obviously, there are more complicated geometries that would be more suitable for our safety critical applications. So going beyond these LP balls, one geometry that people have used a lot for the perturbation set that is also very useful for practical applications is the so-called sparse perturbations or sparse attacks. So what's a sparse perturbation? So take again the same image of on the left. Think of it as a vector. So in a sparse attack or in an L0 attack, we take k entries of this vector, any k entries that we want as an adversary, and we choose, and we can perturb the values of these k entries arbitrarily. Okay, so here k, the number of entries that the adversary can change, is much smaller than the dimension of the input, and hence the name is sparsity here. So these kind of attacks have applications in, let's say, in different areas of machine learning. For example, in object detection, there are the so-called adversarial patches that you see on the right, and these typically cause misclassification. Another application of these kind of sparse attacks is when we is on attacks on natural language processing systems. So here, typically, so for example, consider the application of text classification. So there is a large document, it contains many words, and there are systems that classify these documents, for example, into topics or other things, right? Now, it's often the case that within these documents, you can choose a small number of words, and you can change those words in an adversarial way, such that your classifier will be fooled. Okay, so this paper that you see here is one of the first papers that use this kind of sparse attacks to fool this BERT classifier, which is one of the well-known classifiers or natural language processing systems. So in a sparse attacks, the geometry is quite complicated compared to the simple geometries that I mentioned. So for those of you who have done compressed sensing, you are you know this L0 ball. It's non-convex, non-smooth, and unbounded. That's the geometry of a sparse attack. And because the geometry is quite complex here, one can show that even changing one pixel can fool the classifier. And people have shown quite recently that our traditional classifiers, such as linear classifiers or feed-forward neural networks, actually fail in this setting of sparse attacks. So this is one of those geometries that we need to rethink our architecture design as well as learning procedures in order to provide robust robust algorithms or robust classification methods. Okay, and this rethinking has to be done based on the geometry of the shift. So that's another class of perturbation sets. So one natural question here is that what other classes of perturbations one can consider, which are also important for practical applications? It turns out that there are quite a few of those classes that we can consider. So in addition to, let's say, norm-bounded perturbations or sparse perturbations, one can consider spatial transformations, for example, rotating or rescaling the images, out of distribution inputs. It even turns out that the quality and type of the data acquisition device matters. For example, you can capture the images at training time with one camera, and if at test time you use a different camera with different type and quality, turns out that this shift in type and quality can cause misclassification. And finally, there is a very broad class of transformations, which we call natural variation, which are caused when working in dynamic or natural environments. And since the second part of the talk will be about this class, I'd like to mention a few words about this class of transformations. So here in this slide, the central question that I want to answer is, how does data vary in natural environment? And in order to do so, I'm going to consider a very simple data set, as you see here. So these are this data set consists of around like 10,000 images, and each image is an image of a scene in I think the city of Atlanta, and each image contains a stop sign in it. Okay, and the classification task that we are going to focus on is to classify the stop sign inside the image. Now, there is an important property of this data set, which is that all the images are taken during daylight and in a sunny weather. Okay, so that's the property that we have at training time. So let's remember that. So daylight and a sunny weather. Now, so given this data set, it's a very simple classification task to classify the street sign inside the image. You can, for example, train a neural net for that. So you train a neural net given this data set. And let's assume that you want to use the neural net at test time. Test time here means that, for example, there is a self-driving car. It drives around the city. You want to you take images of different scenes, and you want to use this neural net to basically classify the street sign inside the image. Now, when working in natural environments, the nature doesn't typically give us the same conditions at training time. For example, the nature can add different levels and types of natural variation to the images that we have. So in this case, as an example, the nature can add a snow to the same image. Now, if you look at the image on the right and the image on the left, they somehow correspond to each other. Okay, so they are essentially semantically the same. They are from the same scene, the same street sign. However, they differ in the level of natural variation. One is taken in a snowy weather, the other one is taken in a sunny weather and at daytime and so on. In the same manner, the nature can add, for example, the rain to our image. And we can talk about a variety of natural transformations here. For example, dirty camera lens, darkness, fog, blurriness, grayscale, exposure, and so on and so forth. So that gives us a very broad class of transformations. And the natural question here is whether or not our deep learning based systems are also fragile with respect to these kind of transformations. In order to answer this question, here I've provided some plots, a very simple experiment. So let's consider the same data set as the previous slide. So images that are taken during sunny weather and during daylight. And at test time, so we train the classifier using that data set. At test time, I'm gonna test this trained classifier on data sets that have, let's say, a snow on data points that have a snow in them, and I'm gonna measure the performance. Now, the curve that you see at the top, the orange curve, which is kind of a high accuracy curve, is obtained when testing against data points that are taken using on the same condition as training time. So data points that are obtained in a sunny weather and during daytime. Okay, so the accuracy is high. It's the same condition as training, so there's no surprise here. It's just a success of deep learning. Now let's add a bit of a snow to our images. It seems that, as you see, the performance drops by a few percent. And as you add more and more snow, natural variation, you see that there would be a huge performance drop, as you see. So in other words, our modern deep learning-based systems are also fragile with respect to this kind of transformations. And arguably, these kind of transformations are as important, if not more important, than, let's say, norm-bounded perturbations. So the same amount of effort that's been put to studying norm-bounded perturbations should also be put in studying these kind of transformations and training models that are robust against these kind of transformations, because they are very important for, let's say, our safety critical applications. So the geometry of these kind of transformations is quite complex. Okay, so first of all, we have no idea what the geometry is. We don't have any analytic formulation of the geometry, as opposed to the previous geometries that I mentioned. Okay, geometry is a complex and an unknown surface or manifold, and we don't know what the geometry is. Okay, so that's the geometry that one should consider for these kind of natural perturbations. So during the past few years, I've worked on all these kind of geometries. In this talk, I'm going to talk about the first geometry, like simple L2 kind of geometries, the simplest ones. Here, the geometry is known and simple. And what I'm going to talk about during the talk is the fundamental limits between robustness and accuracy and complexity and overparametrization for these kind of geometries. So as I said, this is the most studied geometry so far in the literature. And since it's known and simple, people have been able to understand a few things regarding this kind of geometries. But I still should say that our understanding on this geometry is still at its infancy, and there is a lot more to be done here. For the sparse shifts, again, here the geometry is known. We know what the geometry is, but it's non-convex to smooth. It's very complex geometry. So we have results here. As I said, we need to rethink architecture designs for these settings. I'm not going to talk about this geometry in this talk. However, I'll be happy to talk offline about this kind of geometry. And finally, in the second part of the talk, I'm going to talk about these natural variation As I said here, the geometry is even unknown and it's also complex. So question is, how can we design robust models? So we'll talk about that in the second part of the talk. So first part will be mostly theoretical, and the second part of the talk will be algorithms mostly, and we will investigate the performance of algorithms compared to the state of the art. Okay, so if there are no questions, I'm going to proceed with the first part of the talk. It's the result of these 3 papers that you see here, and it's joint work with Edgar, David, and Alex from Penn, and Adel and Matthew from USC. All right, if there are no questions, I'll proceed with the first part. Okay, so the first part of the talk will be about adversarial examples. Let's simplify everything. I'm going to consider the Euclidean ball as the perturbation set. So every data point will be basically perturbed within this L2 ball. Okay. Now, in order to explain the concepts, I will have to basically develop this mathematical picture that we had on adversarial examples. And in order to do so, I'm going to talk about the setting of supervised learnings first. Okay, so this is, so nothing in this slide would be adversarial. It's just the good old setting of supervised learning. So I'm going 50 years back and just reviewing the simplest supervised learning setting. So what's supervised learning? In supervised learning, we assume that data, which includes a feature vector X and an associated label Y, comes from some distribution D. The main problem in supervised learning is to find a model that minimizes the expected loss over this distribution of the data. Okay, so here and throughout the talk, by L we denote the loss function. The loss function basically measures the performance of a model theta in predicting the label Y of an input associated to an input vector X. And so the true metric that we need to minimize is the expected loss, where the expectation is computed over the distribution of the data. Okay, so in simple words, how good our model theta is in predicting the label Y associated with an input X. Okay, and this is loss is measured in expectation over the distribution of the data. Now, in reality, we don't know what the distribution of the data is. Instead, we have a data set, or in other words, we have n training data points that come IID from that distribution D, okay? And that's the training data. Now, the common practice here is to relax this expectation into an empirical sum through what we typically call an empirical risk minimization problem, or in short, an ERM problem. So, theta hat, which is the solution of the ERM problem, essentially is the minimizer of the empirical loss measured over the training data set. Okay, so essentially what we have done here is to relax this expectation that you see here into an empirical sum over the training data. And the solution of ERM, the minimizer that you see here, is essentially the model that's the best fit to the data according to this loss function that you see here. So theta hat is the solution of ERM. Again, there has been 60 or whatever 50 years of research into supervised learning. We now have hypothesis classes and solutions of the ERM problem that work really well on test data points that come from the same distribution as the training data. So if your if your data point at test time comes from the distribution D, so in other words, if your input is not perturbed, is a benign input, then your the solution of ERM theta hat works very well. Okay. However, as I mentioned before, it's typically the case that the solution of ERM fails badly on adversarial examples. In other words, the performance of the solution of ERM on perturbed inputs is not really good. It fails badly on these kind of adversarial perturbations. And this is because ERM was not designed to solve our robustness problem. It turns out that in order to design robust models, we need to solve a different objective. And the actual objective that we need to minimize for adversarial examples, to guard our models against adversarial examples, is the following objective. So still the data point comes from the same distribution D. However, the objective that we need to minimize is the expected loss over the distribution of the data of the worst case loss around inside. So for each data point X, we go inside a ball of radius epsilon around the data point, and we look at the perturbation that gives us the worst case loss. In other words, in order to train robust models, we need to find models that minimize this objective. And the inner max that you see here is just a performance, is just a worst case performance in a ball of radius epsilon around the data point. Okay, so for each data point X, we draw this ball of radius epsilon, and we choose a point in the ball that incurs the highest loss given the model that we are using. Okay, now we want to find a model that minimizes this adversarial loss that you see here. Okay, and of course, this model is the most robust model that you can think about, right? I mean, in terms of adversarial examples, the minimizer of this expected loss is essentially the most robust models that you can have. Again, in reality, we don't have access to the distribution of data. We only have a training data set and IID samples from this distribution D. So the common practice in relaxing this expectation is again through the empirical sum that I mentioned. So theta hat epsilon is the solution of the so-called robust ERM problem, which essentially finds a model that is the best fit to the data set in a robust manner. So here the sum is over the training data points, and around each data point, we draw this ball of radius epsilon. Within the ball, we look for the worst case point that gives us the highest loss according to the model that we are using, right? So we want to minimize this kind of robust ERM loss that you see here. And theta hat epsilon is the solution of that, is the minimizer of this loss. Okay, so this solution is obviously more robust than, let's say, the solution of ERM. Let me do a quick recap here of the notation and things that we have introduced so far. So in supervised learning, we solved the ERM problem. Theta hat was the solution of ERM problem. It works very well on test data points that come from the same distribution D as the training data on benign inputs. However, it fails badly on adversarial examples. In order to improve robustness, we had to solve a different problem, which was the robust ERM problem. Theta hat epsilon, here epsilon is the power of the adversary, the radius of the ball. Theta hat epsilon works better on adversarial examples, it's more robust. However, it's been observed in almost for any data set, almost in all the experiments, that the performance of theta hat epsilon, the solution of robust ERM problem, degrades significantly compared to the solution of ERM on benign inputs. In other words, on non-perturbed inputs, theta hat epsilon, which is supposed to be more robust, doesn't work very well. It's robust on the ball, but at the center of the ball, on non-perturbed inputs, on the original data points, it just doesn't work very well compared to the solution of ERM. So there seems to be a kind of a trade-off here. In order to explain this trade-off, I have provided this two-dimensional plane. On the x-axis, I have the standard error performance on non-perturbed inputs, and the adversarial error will be on the y-axis, which is the performance on adversarial perturbations. So in this plane, the solution of ERM, theta hat, lies somewhere here. Its standard error is low. It's good on non-perturbed inputs. However, its adversarial error is high. It fails badly on adversarial examples. The solution of robust ERM is typically observed to lie somewhere here. It's more robust. Its adversarial error is much lower than, let's say, the solution of ERM. However, what's important to notice is that its standard error is typically worse, significantly worse compared to the solution of ERM. So there seems to be a kind of a trade-off here. In order to improve or decrease the adversarial error, we need to pay a price in terms of increasing the standard error and vice versa. Okay, and as I said, this trade-off has been observed in practice, and there are limited theoretical works that basically show this trade. Now, in order to understand pros and cons of adversarial training, there are a few fundamental questions that we need to really answer here. The first question, as I mentioned, is whether or not there is a fundamental trade-off between the standard error and adversarial error, or as people say, there is a fundamental trade-off between robustness and generalization. Why is this question important, and why is this question non-trivial? Because right now, most of the, until a few years ago, most of the results in this area to answer this question was empirical. Typically in our experiments, we saw that there is a trade-off. However, somebody may come and say that, look, I mean, you see these trade-offs because your training algorithms are not good. You don't know how to optimize, or you don't have sufficiently many data points, or your algorithms are not complex enough, and so on and so forth. In other words, there might exist a model, let's call it theta optimal, which attains the best of the both worlds, right? It has a very low adversarial error, and it also has a very low standard error. It's just that you cannot find it. It might exist, but you cannot find it. In order to basically resolve this kind of dilemma, one needs to find fundamental trade-offs between robustness and accuracy that hold no matter what the algorithm is, no matter what the number of data points are, and so on and so forth. So these are called fundamental trade-offs. So the question here that we want to answer here is whether or not we see a fundamental conflict or trade-off between robustness and accuracy, or there is no conflict and there is a model that's essentially optimal or attains the best of both worlds. So that's the first question that we are asking. Once we have the answer to this question, the second question is how can we algorithmically achieve this trade-off using simple and efficient algorithms? And finally, we need to understand the role of other players in this setting. For example, the size and quality of the data, the model size, overparametrization, hypothesis class, and so on and so forth. So I'm going to answer these three questions in the context of Gaussian linear regression. So the problem of Gaussian linear regression, or in short, linear regression, is one of the simplest yet most foundational problems in machine learning and theoretical machine learning. Typically, when there is a phenomenon, people study this phenomenon under simplistic models like the Gaussian linear regression, and typically these phenomenons, typically there are very interesting messages and results coming out of this analysis. And as you see here, once we provide an analysis for this linear regression problem, in the case of adversarial attacks, we will see that there are some interesting messages coming out. So what is Gaussian linear regression? Let me quickly explain what the model is here. So in Gaussian linear regression, the feature vector x comes from the Gaussian distribution. That's the distribution of the feature vector. Here I have, for simplicity, considered the simplest Gaussian distribution, the isotropic Gaussian, just a normal, standard normal distribution. So that's how the feature vector x, the input, is generated. And the label associated with x is given according to this model here. So the label is given as follows. The inner product of x and some ground truth model theta 0 plus some additional noise w that you see here. And this additional noise is just an independent noise that's added. Okay, so the label is essentially obtained through the feature vector in a linear manner, and that's why it's called a linear regression problem. And theta 0 is called the ground truth model theta 0. Now, in linear regression, we assume that we have n data points that are generated IID according to this distribution. And of course, the goal of linear regression is to estimate the ground truth model theta 0 from data. Here we are adding an adversarial component to this problem. So we assume that at test time, every data point x would be perturbed in a ball of radius epsilon. So the adversary has the power to perturb every data point in a Euclidean ball of radius epsilon around each data point x. That's just a simple geometry that I've been mentioning so far. All right, so that's our setting. And in order to explain our quantities, let me explain what the loss function is and how do we basically measure the loss. Given a choice of parameters, a model theta for the regression problem, theta can be used to predict the label of an input x of a feature vector x in the following manner. So the inner product of x and theta would be the predicted label y hat of the input x given the model theta. Okay, that's how the linear regression problem is. And the loss here is the quadratic loss. So the square of the difference between the true label y and what the model theta is predicting here, the square of that would be the quadratic loss. And we're going to study two fundamental quantities here. First of all, the standard risk, which is the standard loss that I mentioned, the expectation over the distribution of the data of the loss. Okay, so that's just the loss that the model theta has on inputs that come from the distribution, the original distribution of the data D. Okay, so performance of the model theta on non-perturbed inputs. That's the usual supervised learning loss, or the measure of the loss that we have. It's called the standard risk or standard error. And also we want to study the adversarial error and the connection between the standard error and the adversarial error. So the adversarial error or the adversarial risk of a model theta would be the performance of the model theta on perturbed inputs. Okay, when there is an adversary which attacks the system and basically adds a worst case perturbation delta in a ball of radius epsilon around each data. Okay, so a standard risk is the standard error, adversary is the adversarial error, and we want to study the relation between the two and whether or not there is a fundamental conflict between these two objectives when we try to minimize them. So in order to understand fundamental trade-offs, our approach has been the following. Let's remember this two-dimensional plane that I mentioned a few slides back. On the x-axis, you have the standard risk. On the y-axis, you have the adversarial risk. Now, for each model theta that we consider for our linear regression problem, you can consider the standard, you can compute the standard risk of the model and the adversarial risk. So that gives you a pair in this two-dimensional plane. Okay, so each model could be basically represented by a pair in this two-dimensional plane. Now, once you put all these points together, you would reach to a region which we call the achievable region for this problem. Okay, so that region is the set of all the points that you can achieve via some model for the regression problem. So all the pairs of standard risk and adversarial risk. Now, in order to obtain trade-offs, what's important to study is the so-called Pareto boundary of this region. So what's the Pareto boundary? This is the boundary of the region that lies on the bottom left of the region. Okay, so this area, this bolded kind of curve that you see here. And the Pareto boundary has the following property. Every point on the Pareto boundary, which is called the Pareto optimal point of the region, has this property. Okay, so consider this point, which is the Pareto optimal point. For every Pareto optimal point, there is no point in the region that has at the same time a smaller standard accuracy and a smaller adversarial accuracy than the Pareto point. Okay, in other words, if you take a Pareto point and if you want to decrease simultaneously the standard error and adversarial error, you would essentially fall outside of the region. Okay, every other point in the region has either a larger adversarial error or a larger standard error than the Pareto optimal point. Okay, so essentially these are really optimal points that you can achieve for this problem. Okay, and this boundary gives you the fundamental trade-off between the adversarial risk and the standard risk. So question is, for the linear regression problem, how can we compute this boundary and whether or not there exists such a boundary? It might be, the boundary might be true or might be just a point, right? And in this case, there is a model which has the best adversarial risk and the best standard risk. If we get to a non-trivial curve, then there is a non-trivial trade-off between the two. So let's see how we can compute the Pareto boundary for the linear regression problem. Now, the good news for the linear regression problem is that this region of achievable points is a convex region. And for that, and because of that, there is a very simple trick from which we can compute the Pareto boundary. And this is called the supporting hyperplane trick. So essentially what we do here is that we look at all the possible lines that are tangent to this achievable region, and the tangent point would give us one Pareto boundary. And if we go over all the tangent lines to this region, we will recover all the Pareto points. Now, so a tangent line would be characterized by this equation that you see at the bottom of the page, lambda times the standard risk plus the adversarial risk. As you vary lambda across from 0 to plus infinity, you essentially sweep the Pareto boundary of this region. Okay, so essentially the problem boils down to finding the solutions of this optimization problem for different values of lambda going from 0 to plus infinity. Second good news is that this optimization problem can be solved exactly as a closed form solution. It takes a few pages to prove and show and obtain this closed form solution. However, I mean, the details are not important. What's important is that we can precisely characterize all the Pareto optimal points of this achievable region for the regression problem. Here in the plot that you see, I've plotted an actual Pareto boundary for a specific regression problem. What's important to see here is that the Pareto boundary is really non-trivial. Okay, you see that there is a non-trivial curve, and this gives us a fundamental trade-off between adversarial risk and a standard risk. In other words, because this curve is a non-trivial curve, there is a fundamental trade-off. Okay, so if you want to decrease the best adversarial risk that you can obtain, you have to increase the standard risk. This is by walking along this curve and vice versa. Okay, and these trade-offs are obtained no matter what your algorithm is, no matter what your complexity is, number of data. These are fundamental trade-offs. You cannot really do better than this optimal curve that you see here. This is the best that you can do, and what's important is that it's a non-trivial curve. Okay, so there is really a fundamental conflict or trade-off between robustness and accuracy, as you see here. So that's the first result. So there is this fundamental limit. The second question that I mentioned a few slides back is that now that we know what the fundamental trade-off is, how can we design algorithms that get close to this fundamental limit of the problem? And in order to basically answer this question, I'm going to consider one family of algorithms that I have already introduced, and this is the most commonly used algorithm for adversarial learning, the solutions of the robust ERM problem. And remember, so theta hat epsilon which was the solution of the robust ERM problem, essentially looks at the empirical adversarial loss given n training data points. You basically look at the sum of all the adversarial losses of around those n training data points. Okay, and we essentially find a model that minimizes this empirical sum. So we're going to study the behavior of these solutions of the robust ERM problem. Here, in order to obtain a family of algorithmic solutions, I'm going to vary epsilon from 0 to infinity. Okay, so epsilon at training time is up to me to choose, right? I can use epsilon to be 0, which in this case, I'm assuming that there is no adversary in the system, and I'm just recovering the solution of the ERM problem. Or I can assume that epsilon is infinity as training is up to me, right? Epsilon infinity, this means that I'm assuming that there is an infinitely powerful adversary. Okay. So by vary epsilon from 0 to infinity, I get a family of algorithmic solutions to this problem. So I'm going to study the trade-off for this family of algorithmic solutions. Okay, let me quickly recall review what our setting was and what's the regime of a study here. So the setting was linear regression, feature vector Gaussian. Label is obtained from the inner product of the input with a ground truth model theta 0 plus some additional noise. N data points are obtained, IID, from this probabilistic model. So N is the number of data points, and P is the number of parameters in the model, okay? Which essentially in the linear regression problem, it would be the dimension of the input. The regime that we study these algorithmic solutions is the following regime. We are asymptotic in N, so we assume that the number of data points goes to infinity. However, what's important to consider is that we assume that the number of data points to the number of parameters is kept fixed. Okay, so this ratio here is typically called the overparametrization ratio of this problem. It's the ratio of the samples to the number of parameters. Okay, so it basically indicates how much overparameterized our problem is. So we're going to study our problems in this regime. And the second theorem essentially characterizes the precise value of the standard risk and the adversarial risk for the solutions of the robust ERM problem in this regime that I mentioned. Okay, details again do not matter. I mean, there is a simple optimization problem that we can solve to find these parameters here. What's important here is that we can precisely compute the standard risk and the adversarial risk of the solutions of the robust ERM problem. Because of this precise characterization, we can obtain, again, trade-off curves, but these are algorithmic trade-off curves now. Remember, I mentioned that we keep this overparameterization ratio fixed. So for different values of delta, you get different curves, different trade-off curves. Now you see here, there are a few messages here. So first of all, this black curve that you see at the bottom of this plot is the fundamental limit. So is the Pareto optimal curve. We cannot really do better than this black curve that you see here. Now, as you see in the plot, as we increase delta, this means that when we have more samples than the parameters, the algorithmic trade-off curve gets closer and closer to the optimal trade-off curve. In other words, when the number of training data points is much larger than the number of parameters, or in other words, the problem is highly under-parameterized, we see that we get very close to the fundamental limit, to the best that we can do. But on the other hand, if the number of samples is much less than the number of parameters, or in other words, when we are in the over-parameterized regime, you see that the trade-off curve gets further and further away from the optimal trade-off curves. So the main message here is that more over-parameterization, at least for this linear regression problem, hurts robustness. So that's one of the main messages that we see that we obtain in this linear regression problem. However, another, again, important point is to consider when we talk about over-parameterization is the distinction between linear and non-linear models, okay? Typically, it turns out that in order to really obtain the benefits of over-parameterization, we need to really go out of linear models, and we need to consider non-linear models such as neural networks and so on. This is due to the celebrated phenomenon of double descent, which was developed by people in TILOS, for example, Misha. So Misha was, and among others, they were the first set of researchers which basically established this phenomenon of double descent. And this phenomenon of double descent was proven by these two groups that you see here on this simple regression problems that I mentioned. So in this slide, there is nothing adversarial. I just want to explain that if we want to see the benefit of over-parameterization, we need to go out of linear models and we need to consider non-linear models such as neural networks. So I have two plots here. This is for linear models, like the linear regression problem that I mentioned. And so here I'm plotting there's nothing adversarial here. So I'm just plotting the best attainable standard risk when you solve, let's say, the ERM, when you consider the ERM solution versus over-parameterization. Okay, over-parameterization is that when the number of parameters become more and more compared to the number of samples. So this is, you see, if you see the standard risk goes up and then it goes down. So that's just the double descent phenomenon. But what's important here for linear models is that the best standard risk that you can attain, it happens when your over-parameterization is very small. This means that when your problem is highly under-parameterized. Okay, so over-parameterization is really not, I mean, it is providing benefits, it's decreasing the error, but I mean, compared to the under-parameterized regimes, over-parameterization is not really beneficial. The real benefit will be seen when we consider non-linear models, as you see on the right. So this is a very simple neural network. I'll talk about it in the next slide. Here, this is again the phenomenon of double descent. What you see here is that the best standard risk happens at infinite over-parameterization. In other words, for nonlinear models, as you increase over-parameterization, you get better and better standard risk. So that's the benefit of over-parameterization for these kind of problems. So, so this was, everything here was non-adversarial. It was about the standard risk. Now, for linear models, I already showed you that over-parameterization hurts. So there is no benefit of over-parameterization. But that's expected. I mean, we see this in also a standard risk. However, in nonlinear models, we saw the benefit of over-parameterization in the previous slides. Question is whether or not for nonlinear models, over-parameterization is also hurting robustness. So that's the question that we're going to answer now. So the simplest theoretical model that people consider for neural nets is the so-called random feature model. So this is essentially a two-layer neural net where the weights of the first layer are chosen randomly. The activation is ReLU, and the weights of the second layer are trained. Okay, this is the random feature model, which is essentially one of the most central theoretical models to analyze the behavior of, let's say, different algorithms or different phenomena for different phenomena. And this is like essentially a toy version of a neural net. Okay, so essentially that's where the theory goes regarding neural nets. So what we studied here was to train this model using the robust ERM paradigm. Essentially, so you have n training data points, and this is your model. You find a model which has this form, which comes from this class, that has the smallest error in terms of the robust ERM objective. And we study the solutions of robust ERM with respect to this model. Okay, again, there is a theorem which precisely characterizes the adversarial risk for the solutions of robust ERM. Again, there is the simple optimization problem which gives you these parameters. To prove this formula, it took us like a while, maybe a year, and like maybe 60, 70 pages. But what's important is that in the end, you get a precise formula that gives you the adversarial risk of the solutions of the robust ERM problem. Now, again, given this precise characterization, you can basically plot the adversarial risk now with respect to the overparametrization as you see here. And this is obtained for epsilon equals 1. What's important to notice here is that the best adversarial accuracy or adversarial risk is obtained where your problem is underparameterized, as you see this point here. So this is in contrast with the standard risk. With the standard risk for nonlinear models, we saw that overparameterization helps in terms of the standard risk. But when robustness comes into the play, you see that overparameterization actually hurts adversarial risk, and it basically increases compared to the underparameterized set. Okay, and this is when the problem is adversarial. And you get similar results when epsilon is 0.1 and for different values of epsilon and so on. So the main message here is that actually for overparameterization hurts even in nonlinear models and neural networks, as you see, may hurt at some cases. All right, so we have similar results for classification. Let me not go into it. So this is the end of the first part. I think I took most of my time. So what we learned here is that there are fundamental trade-offs between robustness and accuracy. And we also studied the effect of overparameterization and show that essentially overparameterization in many cases would hurt robustness when we consider these overparameterized models. And so there is an ongoing work here. So regarding robustness, so we are now looking into non-parametric models. There are very interesting results coming from a group by Kamalika at UCSD, which essentially show the benefit of non-parametric models for robustness, and that's what we are essentially trying to look into for this problem. All right, great. So, well, I finished the first part. The second part is a joint work with Alex and George. I don't think I'll have time for it. What do you think, Arya? What should I do?
You have about 5 minutes or so, so you can probably quickly show some key points.
Yeah. So okay, thank you. So so the main idea. So this is as I said, joint work with Alex and George, published at NeurIPS last year. So they essentially, when we want to, so the second part is about natural variation, or in general, more natural, more general distribution shifts in contrast with adversarial or norm-bounded perturbations. So here there were essentially two important challenges that we had. First of all, we don't have an analytical model that gives us the distribution shift, right? So we don't know how the geometry of the distribution shift is. For example, we don't know how a snow would be added to the image, or whatever, how nature adds a snow to our whatever scenes or images. So that was the first question. The second question is, once we have a model, how can we devise algorithms based on the model that we obtain in order to basically make our neural nets or deep networks robust against these kind of shifts? So longest story short, the basic idea would be to, now that we don't have these models of natural variation, the basic idea is to learn these kind of models from data. Okay, so in longest story short, we would, in a data-driven manner, we would learn a model for distribution shift. Okay, we will try to learn the geometry of distribution shift through the recent advances of generative modeling. Okay, now I'm skipping the details, but that's the core idea. So you don't know the geometry of distribution shift, just try to learn it from data. Once you learn this model from data, essentially you get hold of this manifold or this perturbation set that models the natural distribution shifts. You can use it for to train robust model through a minimax procedure, which is a natural procedure. Let me skip these details here. And the model itself would be, as I said, learned through this recent very recent advances of basically image-to-image translation networks like VAEs and so on. Okay, so just a quick result. So here, I mean, so that's the basic idea. You see that this kind of idea would apply to different domains and applications. For example, here, there's a cool application on medical imaging. So, and let me explain what the shift is here. So here, data at training time is gathered from different domains or different hospitals. That's a domain generalization problem, where so essentially each data point would be potentially cancerous cells obtained from different patients. So these are our data points. However, there is natural variation due to, let's say, change in the color, brightness, contrast, or due to using different devices or different environments and so on. So that's what you have as data, but data varies naturally across different data sets and so on. And at test time, you have data from, again, even a different hospital or different environment. So once you use this procedure, you first learn the distribution shift, and then you use this model of the distribution shift to basically train robust procedures. You see that you would obtain great improvements, significant improvements compared to the state of the art, like algorithms like IRM or Coral or ERM. You get like 20% or so improvement, and that uniformly holds. That kind of improvement uniformly holds on many different other data sets. Okay, let me actually stop here. I've talked too much. Thank you.
Sure. Thank you very much, Ahmed.
Sure.
It was a great talk as usual. I have a few questions, but I will probably go last. And if anyone else has any question for Ahmed, please go ahead. You can either unmute yourself and ask, or you can just put the question in the chat.
I have a quick question. Hamed, thanks for the talk. It's very interesting. So the last part that you didn't get to go into details, I mean, when you say that you learn this model using manifold, I mean, in what sense is the manifold? I mean, how is that represented? Is that implicit just by some latent space, or is it implicit by neural network? Or
exactly. So there is like a generative model. So there is a latent space. Let me actually try to share again. It's a very good question. So let's see. I have a few slides open here. Okay, so here, yeah. So the model, so the model that you learn is kind of a model like this. So it's we treat it as a function, which takes two inputs. The X is the image or the data point. Delta is what we call a nuisance parameter. And the idea is that by varying delta, you get different variations in the image, right? So this is delta is the latent space, essentially the space of delta, and that gives you the essentially the surface or the manifold of the shifts.
I see. And this nuance parameter delta doesn't have to be one-dimensional, or it is.
It's a very low dimensional, yeah, okay. Very low dimensional, like 2, 3 typically in practice.
I see. Interesting.
So just a follow-up in this, like, can you also make this learn this in parallel to training, or do you have to do this sequentially?
So, yes. So far what we do is that we learn this offline, like before training. So you can even use a different data set. You don't need, I mean, any data set that has a snow in it, you can use it to train, for example, these kind of models for, let's say, a snow or some other distribution shift. Once you have the model, you can apply it for your current data set. You can do it also, you can do it in an online manner. This was one of the questions we got in the in Encore. So you can actually do it in a Bayesian or online manner also.
Yeah. You had anything?
Right. No, so in some sense, this delta is essentially your kind of a global parameterization of that hidden manifold in some sense.
Yeah.
So that also assume, because I mean, not all, like even if your manifold is say 2-dimensional, doesn't mean that we can find a global parameterization for that, right?
Yes.
So this is more like a modeling a nice patch in some sense. Very okay. Got it. Very nice.
Yeah, and it's just a model of the distribution.
Right.
Better models would give us better robustness, right? So hopefully, once we get more advanced generative modeling techniques, we can get better and better robustness in these kind of problems.
Thanks.
Sure.
Actually, I have a question. So, so in the regression framework with like linear models, so you showed this like trade-off, right, between two types of errors, and then you showed some results on neural nets, right? So I'm saying like, is there any middle ground? Like, so suppose I have like convex regression or something like that, which is not simple as linear or not as complex as neural net. So what exactly is impacting this performance? Is this the complexity of the underlying map, or what exactly is the?
That's a great question. Actually, let me come up with a simpler version of your question. What I mean, in what sense, or like intuitively, why is overparametrization hurting?
Yes.
We don't know. That's the. I mean, we are thinking about it right now, but I mean, we cannot find a simple reason to show that to basically say that, look, this is because of this reason that overparametrization is hurting. Now, I can give you an intuition. I think what happens is that when you consider adversarial robustness, the landscape, the optimization landscape becomes much more complex compared to the simple standard setting. And this can be seen even in the linear model, right? So the optimization landscape, I mean, linear is not good because everything is linear, but if you introduce a bit of nonlinearity, you see that the optimization landscape becomes very, very complex once you have adversarial perturbations. And we think that's the main reason. And once the optimization landscape is difficult, overparametrization cannot help. It essentially hurts because it overfits and so on. We think that's the main reason, but I mean, so far we haven't been able to like rigorously or mathematically justify it.
I see. Thanks.
Sure.
So is there a way to like, can we interpret this as something like, okay, so this big model or foundation model, like whatever you call them, they're great, but they're brittle,
Right.
in some sense. So maybe they're just memorizing something or a lot of things because due to overparametrization. But then yeah, so did this appear already? Like, did your this overparametrization versus adversarial?
Yeah, I mean, this is a recent work, like 2 months ago. So we've submitted it to PNAS. So we're gonna. I mean, so far we haven't heard anything, which is good news.
Okay, but is this online? Like, did you?
Yeah, it is. Yes.
Okay, great, awesome work. One other question I was thinking about, this adversarial errors, especially when you have, they're not always adversarial. I mean, it's right that I can try to put some patches in exactly the weak spaces or something, but more often they're just random adversaries.
Right.
So when you are taking L2 balls or like or L1 balls, L0 balls, all of these are some sort of worst case. But suppose if you have a probabilistic model on how the perturbation is going to happen, so will all of your results still hold? I mean,
actually no. Okay, so we have a recent paper. I think I have a slide for it. So we call this probabilistic robustness. That's a very good question. Is exactly what you mentioned. So
right, because it's like the information theoretic question.
Yeah, exactly. So essentially, instead of worst case point in the ball, let's ask the following. Let's come up with a model that's good for 99% of the points in the ball. Okay, so let's exclude 1%. And it's often the case that even in practice, people see that. So when you, for example, train a deep network, if you look at the ball around each data point, there is only a small subset of the points in the ball which are adversarial examples. Most of the points are good. So this basically prompts us to basically consider an alternative definition, which is a balance between worst case and average case, right? Which we call it like probabilistic robustness or something, right? Which essentially finds a boundary or finds a classifier, which could look at each data point here, look at the ball around the data point. You can have adversarial examples, but you can allow up to 1% of points that go on the other side of the boundary. Okay, and so we have a recent paper on this. I mean, essentially the optimization problem becomes a bit more complex. It has to do with the row essential soup and so on. You can relax it to these concepts like CVAR, and so on, which are previously developed for row essential soup. You can relax it to CVAR. CVAR is one metric that people typically use for risk sensitive optimization and learning. So it also pops up here, and then you can optimize that. Now, what's interesting here is that, okay, let me actually show you what happens. So once you train with this metric or with this probabilistic kind of way of thinking about robustness, the trade-off vanishes. The fundamental, even we can prove this for the linear regression, but the fundamental trade-off even vanishes. So there is no fundamental trade-off anymore between robustness and accuracy. And in practice, you see this. So you see this clean accuracy. The standard error is 93%, and once you train robustly, it doesn't change. So the clean accuracy doesn't change. So you have a model that has a very good clean accuracy, and it's also good, robust in this probabilistic sense.
I see.
Did I answer your question? Thanks.
Definitely. Looks like there are still a lot to explore. I mean, as you go.
Robustness, in my opinion, right now, this even adversarial robustness that people have thought about too much so far is really in the beginning. I feel that people in machine learning has this, in my opinion, bad habit, as opposed to, let's say, information theorists, that when a problem gets hard, when you make no progress on the problem, just abandon the problem. And come on, like, work on it for at least 10 more years. It's just that I don't think we have obtained solutions that we expect in the setting of robustness. But people,
and you can say a lot about generalization and overparametrization as well, as you are already figuring out those things. Is there any other question?